Hey guys, I thought I'd give you a short video about how to do part 2 of the conservation of momentum lab, where you collided those two carts into each other. Some parts of it we've already talked about in class, but just in case you forgot and need a brief rehashing. The data that you collected for that looked like a graph of position versus time, or at least that's what it's supposed to look like. And so you'd have one slope and then a second slope. All right, the first slope is going to correspond to the initial velocity, right? Steeper slope because before the collision it was moving faster. And then presumably after the collision it ought to have slowed down, so there's your final velocity after the collision is that other slope. Okay, so based on these numbers, when it says in the calculations for like experimental values, right? The second one says, find the ratio of final and initial kinetic energies. For your initial kinetic energy, you ought to be able to do something like this: 1/2 m1 v1 squared. All right, where v, I should say v initial, right? Where that's the kinetic energy of the moving cart before the collision. K final, 1/2 m. All right, after the collision, it was a perfectly inelastic collision, so the mass you are using is the total mass because they're stuck together. So m1 plus m2, and then of course the final based on your graph, right? So if I had some made-up numbers, if m1 here was, say, 500 grams, I'd have like 0.5. If the slope here, vi, happened to be something like, I don't know, 0.5 meters per, let's make a different number. How about 0.6 meters per second? Then there you go, there's 0.6 going in there. All right. If after the collision, if m2, let's say, was 1 whole kilogram, right? m1 plus m2 would then be 1.5. And if the velocity after the collision were like 0.18, say, then there you go. You'd plug in 0.18 there, calculation. All right, where it says ratio of final and initial kinetic energies, a ratio is always a fraction. So if it says calculate the ratio kf over ki, then that's what you're doing. You're taking whatever this number is divided by whatever this number is. Okay, so that's the part that is I guess number 2 in the calculations under experimental values. All right, now, the part that I figured people would have a little more trouble with is where it says ideal values, knowing exactly what they're supposed to end up with. The ideal values part is basically like you're doing a physics textbook problem, right? If I gave you something like m1 equals 0.5 kilograms, and this cart is moving along at 0.6. I'll just use that number that I wrote down above from the graph. All right, and m2 equals 1 kilogram. All right, what would the final velocity of the system be if the collision is perfectly inelastic? So that's what you're doing, is just basically a textbook problem. So you'd set it up the same as a textbook problem, right? If the only one that's moving is m1, then you'd stick with the momentum before the collision is m1 v1. That's going to equal the momentum after the collision. And if the two carts are sticking together, then you're doing m1 plus m2 times v final. So if you then solve for v final, it's m1 v1 over m1 plus m2. There you have it. All right, now that should actually hold true for all of your collisions. Just m1 and m2 and v1 are going to change. All right, so like for the first run, m1 and m2 are equal values or whatever, and you wrote those numbers down. The question you might have is, well, what do I use for v1? You are going to use the initial velocity that you got from your graph. So that's the only number, well, that's not true. The masses and that initial velocity are the numbers that you will take from your experiment like from your actual data, and plug in. Okay, and then that should spit out a ideal final velocity. Now, with the bogus numbers that I made up here, the final velocity ought to be 0.2. All right, in real life, it seems that for my made-up data here, the final velocity was 0.18. And so they're going to be different, right? So you may get my final velocity is supposed to be 0.2, but you actually got, 0.18 or something like that based on the slope of your graph. That's what I'm having you look at, is the difference between the ideal values and the experimental values, and then maybe hopefully trying to arrive at some kind of reason for why those are different. Okay, so that's the first part of under ideal values, where it says final velocity, find all that stuff. When it says ratio of final and initial kinetic energies, again, you can derive a formula for that, but it's this stuff up here, right? K initial, K final. If you look back at your notes, there was a specific formula that we came up with, which you may derive in your work and show what that is. And use that over and over, or whatever. You can calculate numbers for those things and get Kf over Ki using your ideal final kinetic energy. All right, and express that as a percent, and there you go. Then you're done. Okay. I think that's hopefully clear enough. If it's not, please email me with further questions, but I think that should be enough of an introduction to how to do part 2 if you were confused. But please email me with more questions. Thanks.